Welcome friends to this session of our discussion. In the previous session we have discussed about the HJB equation, Hamilton-Jacobi-Bellman equation. This equation we have derived using the principle of optimality and particularly for a continuous time system. We have derived the equation del J star by del T plus H. This is my optimal value of the H, because the optimal U I am utilizing here. So, with optimal value of the U, this is my Hamilton-Jacobi equation, which we have to solve with the terminal condition, which is J star x star of Tf equal to S of x star Tf, and this boundary condition is known to me. So, in this discussion we will apply the HJB equation to my LQR system. Means we will consider a linear time invariant system, or it may be time invariant or time varying. So, we are applying HJB equation to my LQR system. We are considering the system as x dot t equal to a txt plus bt ut. So, we are considering a time varying system, and the performance index we have considered as a quadratic performance index defined as half of x prime tf f of tf x of tf. So, this f should also be the function of time, which is missed here. So, this is the f of tf plus half of t0 to tf x transpose t qt xt plus u transpose t rt ut dt, which is our standard as we have considered in the previous case. The same system and the performance index we are considering here. What is my HJB equation? HJB equation is J plus H. So, first of all I have to define what will be my Hamiltonian, and what is the Hamiltonian? We have defined the Hamiltonian as, if you recall, H we have defined as my V plus del J by del X transpose F x ut, or F dot we can write. So, this is the V plus del J by del X transpose, or simply we can also write as V plus Gx star transpose F. Now, in our system which we have considered here, it is a linear time varying system. So, this is my F is ATXT plus BTUT is nothing but my F, and V is x prime Qx plus u prime Ru. So, we are defining this H at a journal control point ut we have considered as half x prime Qx plus half u prime Ru. This is nothing but my V plus Jx prime ATXT plus BTUT, which is nothing but my F. So, we can define Hamiltonian in this way. My next step is I have to find the optimal value of this H. This means del H by del U must be equal to 0. So, for optimal U, my del H by del U is 0, which gives me RT ut plus B prime Gx prime xt t, this equal to 0. So, I got this equation if I am differentiating this H with respect to U. So, my this first term is independent of U. So, this will give me 0. This is a quadratic term in U. So, this gives me Ru, and J prime AT xt is independent of U. So, this will be 0, and J prime Bu. So, this will give me B prime J. So, this we are getting as B prime J, should be Jxt. So, by this equation I can find out my U star as minus R inverse B prime Jxt. Now, if I will substitute this U in this H, so I will get my optimal value of the H. So, in the next step we are finding the Hamiltonian by substituting the value of the u star in H. My first term remain the same, half x prime q x, this is u prime. So, what we have taken, my optimal u is minus R inverse B prime Gx star, and the term which we are placing, that is the half u star u prime Ru, which is my second term of the Hamiltonian. So, if I will take the half of u prime is Gx star prime B R inverse is giving me the first term u prime, then I will have the R, then u is R inverse B prime Gx star. So, u prime Ru I can write in this way, this will be my unity. So, this is nothing but with minus half Gx star prime B, I am dropping the T, B R inverse B prime Gx star, and this we are writing as my second term half J star prime B R inverse B prime J prime. Now, what is the next? J star AXT, by multiplying this J star with the first term. So, I got this term as J star AXT. My next term will be J star BT and multiplied with UT. So, this is J star prime BT UT, and UT we replace with, so this is J star prime BT U R inverse B prime Gx star. So, my last term is Gx prime B R inverse B prime Gx star. So, these two term, if you will say, this is the half of this and this is 1 times of this. So, by subtracting by these two terms, I get minus half of Gx star Bt R inverse B prime Gx star plus Gx star At xt. So, this is my optimal value of the H. If this is my optimal value of the H, so I can write my HJB equation as Jt plus optimal value of the H equal to 0. This is the Jt. What is the optimal value of H? Is my half of x prime qx minus half of j prime B R inverse B prime Jx Gx star At xt equal to 0. So, I got this as my HJB equation. So, my HJB equation, I have to find out the value of the J star. I have to solve this equation with my terminal condition as J star x of Tf, Tf as half of x star Tf, f of Tf, x of Tf. So, for a linear system, for non-linear system, no direct solution you can get for this HJB equation, then we have to solve these equations using the numerical techniques. But for a linear system, as we have seen, my terminal cost, at the terminal my cost function is J star x star of TF which is equal to a quadratic function of x. So, I can assume a solution which is similar to my terminal solution, and this is nothing but j I am assuming as half of x prime p x, where this optimal cost is a function of x and t. If j is a function of x and t, so I can find out del j by del t and del j by del x. What we are saying? We are assuming the solution of HJB as let the optimal cost is half of x prime p x. So, I am assuming my cost as this, which I have considering analogous to my terminal cost, and with this value of the j I am finding out del j by del t and del j by del x. So, with this my del j by del t is half of, because x and t are my two variable which we are considering, p is a function of time. So, this will be half x p dot x, and del j by del x is simply my p t x t. So, this j t and j x I am replacing by half of x t p dot t x, I am replacing the j t by this. So, my HJB equation now will become, so my first term is the j t I am taking as half of x prime p dot of t and x t. So, this is my j t. My next term is half x prime q x plus half x prime q x. Next term is minus half of j x prime b r inverse b prime j x, and what is the j x? My p t x t. So, half of j x prime is p t x t. So, I am writing this as x prime t p t, because in this case again the p t we have considered as a symmetric positive definite matrix. Then j cost, because why positive definite? Because j must have some positive value of the cost. If my minimum cost cannot be negative, so cost will be positive. So, p will be x prime x is a square term, p should be a positive definite. So, if p is the positive definite and symmetric as we have considered in the previous case, the same analogy we can take it here. So, transpose of this will be x prime p b r inverse b prime j x is p t x t. This is my third term of the HJB equation, and the last term is j x prime a t x t. J x prime is x prime p. So, I can write this as last term plus x prime p t a t x t equal to 0. So, the HJB equation given in this form with my assumed solution as j as half of x prime p x, I find out j del j by del t del j by del x. Substituting this value in this equation, I am getting my equation as HJB equation as half of x prime p dot x plus half of x q x minus half x prime p b r inverse b prime p x x prime p t a t x t. So, now if you will see the first term is quadratic and symmetric, second term is quadratic and symmetric, third term is also quadratic and symmetric except the last term. Last term will have my p t a t, p is symmetric, a may be any of the matrix. So, we are using the principle that let if A is any square matrix, then A can be written as A1 plus A2, where A1 is symmetric and A2 is skew symmetric. Then A1 will be A plus A transpose by 2 and A2 will be A minus A transpose by 2. So, any matrix I can write in terms of the its symmetric form is giving me the A plus A prime by 2 and A2 is given as A minus A prime by 2. So, the matrix PT given here we can break up as half of PTAT transpose of PTAT plus half. So, this is my symmetric term and half PTAT minus transpose of PTAT is my skew symmetric form. So, this PTAT I can represent in this because my all terms are symmetric. So, the only part of this matrix which is useful, that is my symmetric part, because the skew symmetric part is multiplied with the function x prime half of PTAT minus PTAT prime into x. So, this will vanish and we are left only with this symmetric part. So, I can replace PTAT as half of PTAT plus PTAT prime. If I will replace this, so I will get the half of x prime PTAT plus half of x prime transpose of PTAT is A transpose P x. So, now I can convert my this whole equation in terms of this equation, and this equation if you will see can be break up as half of x prime t, I have p dot plus q, p dot, this will be t plus qt minus p b r inverse b prime p plus pt at plus A transpose t pt multiplied with simple x t must be equal to 0. So, for any value of the x t, because x t may be arbitrary, so I can say what is there in bracket. So, this equation to be 0, my this whole term must be equal to 0. So, I can write as p dot t plus q t minus p b r inverse b prime p a plus a prime p equal to 0, or p t I can write simply in terms of as minus p t a t minus a prime p plus p b r inverse b prime p minus q, and this is my well known matrix differential Riccati equation which we have proved also which we have also derived using the calculus of variation approach. So, once the p is known, my u was minus r inverse j xt t, this was my u. So, this u will be nothing but my R inverse B transpose T P T x t, because this solution is nothing but my P T x t, and this I can say as minus K T x t. So, I can have the closed loop feedback control where my K T is nothing but R inverse B prime P T, and P T is nothing but the solution of my matrix Riccati equation. So, using the HJB equation also we can have the closed loop feedback control. So, this is the application of the Hamilton-Jacobi-Bellman equation to a continuous time system. Now, up to this point we have made our discussion in which we have not considered any constraint to any of our variable, neither on the u nor on the x. So, at the end of our course we will consider one problem in which we are going to constrain the u and see how the constraint on the u will change the solution of my problem. So, this constraint optimization problem we use the Pontryagin minimum principle. So, we will discuss this principle. Say in a given system, if you will consider any system and consider a variation in the control, means my control is varying from its optimal value u star t to delta u t. With this variation we can find out what actually is the increment in the system or the functional and what is my first variation, if you will try to find out this. So, as we know by definition my increment is defined as j at a given value of the control minus j at the optimal control, where u t is u star plus delta u. Now, this j u t can be expanded as Taylor series. So, what we can write for j u star t plus delta u t, because this is the value of my j u t. So, this will be nothing but my j u star of t plus del j by del u delta u, the first order term, plus higher order term. This will appear as my expansion, and once I will subtract j u star u t. So, I will left only with the delta j u star of t plus the higher order term, and by the minimization principle, if my cost function is minimum, then my increment must be greater than or equal to 0. So, once we will, and in this we will write our first variation delta j as del j by del u into delta u. So, for optimal cost my increment should be greater than 0, and in case of the unconstrained system, what was our condition? This means my first variation must be vanishes, means we considered del j equal to 0 if my u is unconstrained, and the sufficient condition is second variation must be positive definite. So, if I will write the increment, this will be the summation of my first variation plus second variation which is positive. So, this means j is always greater than equal to 0. So, my fundamental theorem is at optimal value of the u, if u is unconstrained, then my first variation will be 0, but if u is constrained, constrained means if u is constrained, this means ut will have its limit with say u minimum to u max. So, this is if my u is constrained, then I can't say my delta u will be arbitrary. So, delta ut is not arbitrary if external control u is constrained. So, assuming that all admissible variation means delta u is small enough that the sign of the increment delta j is determined by sign of variation delta j. This means the sign of this increment. So, what we are saying, if my delta u is not large enough, then the sign of delta j will be determined by the sign of first variation, because all other higher order term will be smaller than the first variation. So, if u is constrained, u is unconstrained, then my first variation is 0, then the sign is decided by the other variations. But if u is constrained, then my first variation will not be 0 and the sign of increment is decided by the first variation. So, this means I can say the necessary condition for u star to be minimized, then my first variation must be greater than or maximum equal to 0. So, only 0 condition is not applied if my u is unconstrained. And if I will find out the delta j, the first variation which is T0 to Tf del h by del u into delta u, if I am defining representing my problem in terms of the Hamiltonian, that this is del h by del u, delta u will be my first variation in delta j. As we have seen before, we can apply the Lagrangian approach or the Hamiltonian approach, and if we are using the Hamiltonian, we can write delta j in terms of the Hamiltonian as del h by del u transpose multiplied with delta u. This means del h by del u, delta u can be written as h at the variation point minus h at the optimal point. So, this is the meaning of my del h by del u. This means delta j is h at variation point and the h at the optimal point, and this del j must be greater than or equal to 0. This means my right hand side of this must be greater than or equal to 0. This shows that if I will have a h at a variation point, this value will always be greater than or equal to the value of the h at optimal point. So, this means if I will minimize the h at any given control, I can minimize this u within the constraint of u max and u minimum, then I will get whatever be my optimal value of the h. And this is the Pontryagin minimum principle, means the Hamiltonian we have to minimize with respect to u to get the optimal value of my Hamiltonian, because this Hamiltonian at the u point and this Hamiltonian at the u star point, minimization of this Hamiltonian giving me the optimal value of my h, and this is my necessary condition for the constraint optimal control system, that the optimal control should minimize the Hamiltonian, and the sufficient condition is my second derivative of this h must be positive definite. So, this Pontryagin minimum principle we can directly apply to the constraint system. In the next class we will see that how the constraint system, this Pontryagin minimum principle can be applied to the constraint system and will be used to solve the minimum time control problem. Thank you very much.